All right, let's get started. So now we're going to start to actually see a lot of the advantage of a lot of the three-phase power and AC circuits and apply them to the real workforce, which is AC machines. And AC machines are seen everywhere. If you look at EVs, and I know EVs aren't the popular thing right now, but EVs use the same concept of AC machines. They actually, if you believe the Tesla folks, Tesla started out as an AC induction machine, essentially, and it's now switched to a permanent magnet synchronous machine because it has higher levels of efficiency, but it's still an AC machine. So we got to understand the concepts. Sorry, I'm still coughing from last week, but we want to utilize the concept of an AC machine. So we have to understand a little bit about the magnetic fields. If you remember the stuff from chapter 1, how we had magnetic fields flowing, we're going to apply that here, but with three-phase AC, we talked about a really easy way to develop a rotating magnetic field. And so we're going to see how we can do that, or we can develop that really quite easily with an AC set of incoming phasers. So we always have to have alternating, right? Either we mechanically make it by doing a pole swap or a commutator swap, or we can just take advantage of the fact AC is always changing, and we can get our magnetic fields really just from the AC source. And an AC machine is called a machine because it can be a motor, as in the case of a load, or it can be a generator, as in the case of a source. Really, it's a power converter, essentially, but that's the idea. And so AC machines, you can buy an AC motor or an AC generator, and it's the same piece of equipment. It just depends on the input and the output power. And they are predominantly found in industrial facilities. We're talking about three-phase AC machines, not single-phase ones. AC machines, we find them big time in industrial facilities. We even talked a little bit about, some of the bigger restaurants where you need a lot of power. That's the type of applications that you'll find them. So we got to use our right-hand rule because we're looking for that orthogonal vector. So we take our finger, we point in the direction of the magnetic field. Our index finger points our middle finger points in the direction of current, and our thumb is in an orthogonal plane or direction from that. And that's where we're going to have motion. We said force before, but now we actually have motion because we're trying to rotate something. So here's the key thing about this, the polarity. So voltage polarity. How do we get voltage polarity? It depends a little bit, but if you're trying to create what's called a back EMF, it is the polarity to drive the current direction as specified by our right-hand rule. This is in the case of generator action. So without getting into a lot of specifics, this is from the Chapman book. You can take a look. But if we're trying to get an induced voltage across a coil of wire, right, because we're trying to make a generator, so the generator just has rotating coils of wire in a magnetic field, we create a voltage that looks like this. This is an induced voltage, and it's pretty darn sinusoidal. Looks pretty good for a sinusoid waveform. If we want to do the opposite for a motor, we use the left-hand rule. So let me move this down to the bottom over here. And again, this essentially what we're looking for is we're pointing our direction. So we get our values here, and then we get our corresponding thumb in the orthogonal direction. It's always perpendicular because that's the thing about Fleming's left-hand rule. We're always looking for a perpendicular or orthogonal vector, and our torque has to be rotational. We can't really make a linear motor. I mean, we could, but eventually we'd run out of room on the track. And so all the applications we're talking about are rotational. So we're going to talk about torque instead of force. Same book. And instead of having a value for, geez, why can't I talk? Instead of having a value for voltage, we're going to have an induced torque that again looks sinusoidal. And this is just for one particular phase. When we add the three phases together, we're going to end up with a constant torque, which is really desirable because if your torque is not constant over one cycle, you get something called vibration, right? If the torque is bouncing around up or down, increasing or decreasing, the load is going to try to speed up or speed down accordingly. And then you get vibration, which is usually not a good thing. Things break, they don't last so long. So we're trying to avoid that. All right, so now we're going to take the rotating magnetic field. We're going to see how we can create this. And we're going to create this by locating 3 coils of wire, A and A prime, B and B prime, and C and C prime. They're located on the perimeter of our motor. So the motor, if you can understand, is going into the page. So you're looking at the end of the motor, and then you see the 3 windings for current to go through. Obviously, you have to have an out and back because it has to be a continuous circuit for current, right? So A is assuming going in, and A prime is going out. B is going in, B prime is coming out, and C, it's going in, and C prime is going out. All right. Now, what I mean by that is that the winding is going C, it goes down and then loops back and comes out. So if you could envision just one loop or winding going down and back, you can see the perspective of it. Now, that does not mean that the current is going in that direction. It just means that that's the direction of how the windings are configured. This is really a simplistic view because we only show one winding. In real world AC machines, you have windings located about the perimeter of the shaft, but we can generalize and just say, well, if it's located along the shaft, we'll have the A phase represented essentially in the middle. All right, so just show the one winding in the middle. The other really important thing too is look at the electrical spacing. To go from A to B, I have to rotate, and this might be a little confusing, but I have to rotate 120 mechanical degrees. Physically, I am physically rotating 120 mechanical degrees to be able to get to my B winding. And then my C winding is another 120 degrees away from the B winding. Conversely, I can also go in the opposite direction, another 120 degrees to get to my C winding. So this is the key thing about building AC machines. If you want them to operate properly and to look like a balanced load, you have to locate them so that they're spaced 120 degrees apart. The prime winding, you don't have to worry about the prime winding being 120 degrees apart from any of the windings because that's the return path. We're only talking about the one winding that goes out. It's going to be 120 degrees separated from the other 2 windings. Now, we have to energize the machine. And we're going to energize it from a 3-phase power system that's balanced. How do we know it's balanced? Because it's 120 degrees apart. So if you can imagine the phasor diagram, this is the current. This is IA, IB, and IC. Those are the 3 phasors, and they're always rotating, right, in a counterclockwise direction. So you have 2 things here. You have the physical windings separated by 120 degrees mechanically, and we also have the electrical currents separated by 120 degrees. But there's no mechanical with the electrical currents. It is only electrical separation. So we have to start understanding that there's a huge difference between mechanical and electrical. The mechanical is a physical, where the electrical is a phase relationship. So you can see the 120 over here, or if you wanted to do sine waves, we see that we have 120 degrees of separation over there. That's essentially what that means. So this is electrical, where the previous page is mechanical. And why is that important to us? Because we don't have to have 120 degrees of mechanical separation to get 120 degrees of electrical separation. That sounds a little crazy, but in actuality, oftentimes they're not. And we'll talk about how we can adjust the speed, the nominal speed of operation of an AC machine, just based on monkeying with the mechanical separation of things. And do we get 120 degrees electrically? So these are the currents going into those windings. And when we have currents that are like this and a physical configuration like this is hugely important. When we sum the magnetic fields, the individual magnetic fields, because of each of those current flows, that sum of those magnetic field is always going to have a value of 1.5 times the value from any one, the maximum contribution from any one phase in operation. Okay. Why is that important? The 1.5 isn't that important. But what is important is that it always is, no matter where you are in your sine waves, your electrical sine waves, any of these, you're always going to get 1.5 times your value. Remember, we talked about trying to maintain a constant torque. You don't want your magnetic field to go up and down, because if your magnetic field goes up and down, then the output torque is going to go up and down. So our magnetic field had better be constant, or else, we can't produce constant torque. So, excuse me, where do we get a magnetic field? We can't use Fleming's rule because now we have a wire that has a direction that's changing, right? The wire goes into the page and then comes back out. Anybody here into bow and arrows? One person? When you're shooting at somebody or you're getting shot at, an arrow's coming your way or going away from you, what's a good way to tell if you could figure things out really quickly? Duck and run or stand there and smile? How do you know if you're going to be safe if you need to duck and run, or you're going to be safe? Okay, if I'm shooting an arrow at you, what's the first thing you see? The tip of the arrow, right? If I'm shooting away from you, what's the first thing you see? The quivers, right? The arrow quivers, right? They used to be feathers. I don't know what they're made out of anymore. So we apply that, I don't know if this is a great analogy or not, to show a three-dimensional item here in 2D. This is the tip of the arrow. Current is coming out of the page. This is the quivers. So the current would be going in the quiver part and coming back out here. Why do I do that? Because now I take my hand, I'm going to take my right hand, I'm going to put my fingers pointing in the direction of where the winding would go, the current would go, I should say, through the winding. I wrap my fingers around where the winding comes out, and my thumb points in the direction of the magnetic field that would be generated because of positive current flow flowing in that winding. So if this is winding A and A prime, then positive current going down, returning coming out, gives me a magnetic field as shown, right? And I'm just showing general vectors here. I'm not actually showing any magnitudes of current. I'm just showing the vectors. I do the same thing for B and B prime. Notice 120 degrees of separation. My fingers point in the direction of the quivers, right? Because that's where it's going in. I wrap around in the return direction. My thumb points in the direction of the corresponding magnetic field because of positive current flow. B sub B means it's just the magnetic field B corresponding to phase B current. And lastly, C and C prime. Again, I'm going another 120 degrees, but I take my right hand, I point in the direction of the positive current flow, it wraps around, and my thumb points in the direction of the corresponding magnetic field. Okay? That's how I would get magnetic fields from the three. Make sense? Does it make sense? Sort of makes sense? Because it's pretty important. We see how when I run positive current in this winding, I wrap around, my thumb points. It's basically giving me another orthogonal vector. I'm looking for that perpendicular vector to get those values. And then at the end, I'm going to solve for a net magnetic field, which is going to be the sum of those three. Okay. My net magnetic field, the north-south that exists inside that machine, is determined by summing those together. Okay. So if I have a net magnetic field, that means I have a magnet inside the machine. Every magnet has a north and a south pole, right? So in this configuration, I'm only going to generate one north and one south. So this would be called a two-pole machine. Why is it two-pole? Because it has one north and one south. But I can make four-pole machines. I can make six-pole. I can make eight-pole, 10, 12, on and on and on. Notice I didn't say I could make a nine-pole machine. Why can't I make a nine-pole? Can you have a north without a south, or a south without a north? With magnets, you have to have both, right? You have to have two poles. Nobody's ever found a unipolar or monopolar machine. So you always have to have an even number of poles. You'll never have an odd number. And we'll start to talk about synchronous speed of operation, but it's going to be solely based, well, not solely. Synchronous speed of operation is going to be based on the electrical frequency of the machine. And we'll talk more about that when we look at that. All right, let's see this in motion. So we have a machine here on the right, and you can see I have my three currents going in here, A, B, and C. A is going to be some cosine of omega t. So this is A. B is going to be cosine of omega t plus 240. And C is going to be cosine of omega t plus 120 degrees, right? You can see how they're all phase shifted by 120 degrees. This one peaks at 0. This one peaks at positive 120. And this one peaks at positive 240 or minus 120. Right? So now our electrician friend is going to go ahead and wire up phase A, phase B, and phase C to the machines. And in actuality, most cases in the real world, those are going to be all internally connected. That's going to be a common neutral point. So they'll all be internally connected. So the electrician only wires phase A to the terminal A on the machine, on the machine. Phase B to terminal B, and phase C to terminal C, except we don't really call those terminal A, B, and C. We'll call it terminal 1, 2, 3, or X1, X2, X3, and we'll see why in a minute. All right, so let's put this in motion. So this is at 0 degrees. Now we're at 90 degrees. 90 degrees, what has happened? Well, my phase A current is this value. My B current is this value. And my C current is that value. Look at the previous case when I was at 0 degrees. My phase A was here. My B and C are at the same value. Everybody notice those are minus 0.5. So do you remember before where we had our machine? We had A, let's see. I had this backwards. This is A prime, sorry. Oops. A, B, C. So this here is, we'll call this terminal down. We'll call this terminal X1, X2, and X3, and these are our neutral connections. All right. So in terminal 1, when the current is at 0 degrees, we have maximum amount of current going through there, right? It's at the peak of its sine wave. Notice the size of the quiver and the circle. They're at their largest value they can be because the most amount of current is going to be going into that terminal X1 winding. Look at terminal X2. Why is the current coming out? Remember the concept of the arrow? It's the point. We see the point first. So the current is coming out at us. But why is the current coming out when that should be what the electrician wires X2, phase B to X2? Why is that a B? Yes, sir. Yeah, very good. It's negative 0.5. So negative 0.5 means the current is not going in here. It's coming out. So you'll notice that the actual dot is smaller and it's coming out of terminal 2. Same thing for terminal X3. Because remember, this should be X3. We should have positive current, but because of the negative 0.5, we see that current is coming out. So we can go ahead and take our hands, going into terminal X1, and returning on the return of X1, our thumb points at a maximum in the 0 degrees. Now we go to B. B points down. Points up because we're going in, points down. Here is our magnetic field for B. And we do the same thing for C. Current goes in on the bottom, thumb points in the direction. This is B sub C. When I add those together vectorially, this plus this plus this is going to equal that. They're going to sum together. You can see how the ones that go up and one go down, those Y values will cancel each other out. And all I get is the 1.5. We'll show the actual calculations in a minute. All right, we see that for 0 degrees. Let's look at 90 degrees. So 90 degrees, my current through phase A is 0. Take a look in my A winding. Is there any dot or X shown in there? There isn't, so there's no current going through there. Now B is a negative 0.866. So it was negative 0.5, now it's 8.66. So it's going to be a bigger value, not as big as the A was at the 90 degrees, but bigger than it was before. So I take my fingers, I wrap around and point. This is B sub B. Now C is a positive number. So remember, this is X1, X2, and X3. So positive current is going into the terminal X3 because of the C connection. I wrap my fingers around, and this is B sub C. When I add those two vectors together, one like this plus one like this, I end up with something that looks like this. Why is that important? Because electrically, I've rotated 90 degrees, right? I started out at 0, and then I went to 90 degrees. Magnetically, I started at 0, and then I rotated 90 degrees. And so what we're going to learn is magnetically also means mechanically. We're going to get mechanical rotation corresponding to that as well. So now let's see that. I thought I had a GUI here. Let's see it over here. We'll rotate it. And you can kind of see the currents going in. And you can see the relative magnitude. And you can see the corresponding vectors. And then the black is the net magnetic field. So you can see it rotates around a full 360 degrees. And it just keeps rotating forever. Yes, sir. It's always going to be 1.5 times B sub M. The magnitude never changes. It rotates, and we need it to rotate, but its magnitude never deviates. Always 1.5. Which is what we want, because for the magnetic field, we have a north and a south. If we have another north and south on this shaft or inside this machine, and we allow it to rotate, then they're going to chase each other, right? And if you look closely over here, that's the stationary part of the machine. On the bottom of this, this is connected to some sort of pedestal or something like that, a concrete pedestal, it's not allowed to move. If you notice inside, there's a little gap, an air gap between the stationary part and that part. This part is allowed to rotate, and it's going to allow it to chase. So as long as you have a north and south on that rotating part, the north and souths are going to try to line up, aren't they? And they're going to chase each other. And so, again, this is a really good thing because you have that constant magnetic field at 1.5 rotating around at whatever the speed is, but it always has to rotate 190 degrees electrically to get 90 degrees mechanically, 180 degrees electrically, 180 degrees mechanically, and on and on and on. If I can make the rotating part have a constant magnetic field, then they're going to always operate. They're always going to chase each other, and it's going to have a constant amount of torque. Here's the math behind it. If I start out with 3 currents, right? So here is my currents flowing through. Where did I get these numbers from? Do you know? Where did I get the angle of 0, angle of 240, angle of 120? Doesn't this have an angle of 0 degrees? For positive current going in there, it should always create a magnetic field that's always at 0 degrees. Over here, positive current in the winding that has the B current should give me always minus 120 degrees or 240. Same thing with C. Positive current into the X3 terminal is always going to give me a positive magnetic field as shown in that direction. So where did I get these? That's A, that's B, and that's C. I got those angles from where the positive current gives me a magnetic field. Where did these come from? Sine of omega t, sine of omega t minus 120, sine of omega t minus 240, or plus 120, doesn't matter. Where'd those come from? From the currents. The current flow going through those windings is going to impact the magnitude that you're going to get from your magnetic field. And if I can get some maximum current flow to give me a maximum magnetic field, then I can say, you know what? I'll just create that maximum magnetic field instead of writing it as current. I'll write it as a function of the maximum magnetic field, and then I'll just multiply it by whatever the current, where the current is on its sine wave. So I got this one from the winding configuration, and this one's from the current. That's why I get those two values. How did I, next step? Well, I know over here, I can do Cartesian coordinates. So for phase A, that's BM cosine of 0. I said 0, but then I wrote theta. I did it again. Plus J sine 0. What's the cosine of 0? 1. What's the sine of 0? 0. So this here is just going to be equal to BM times the sine of omega t, and it's only going to be in the x direction. There's only a real part. There's no imaginary part. I do the same thing for the 240 degrees, and I end up with negative 0.5 plus a negative square root of 3 over 2. Everybody buy that for $1? See where I got that? If you're not sure, let me bring up whiteboard. See if we can go back to our values and draw things out. Okay, wake up. Okay, so let's draw an XY graph. And 240 degrees is going to be over here, right? It's going to be about 30 degrees from that 90 axis, correct? So we know that this is the cosine axis minus cosine axis, sine axis, minus a sine axis, right? So if you take the cosine of a vector that's in quadrant 1, you're going to end up with a positive cosine and a positive sine. Quadrant 2, negative cosine and positive sine. On and on and on. You all remember that from maybe trig or pre-calculus? I'm not exactly sure. So the question is, how can I do this? Well, I can do one of two things. I can just say Euler's identity, which is, whoops, I did it again. I don't know what happened. What was that cheat key to switch back? What did you call it?
Windows P.
Windows P. But it isn't because I don't see it on the screen. Still not duplicating. So if I go PC only, now duplicate. No, it seems to be working. I don't know why it's not working, but the new Microsoft feature. We won't call it a bug. We'll call it a feature to add some confusion to you all, or to me at least. So what we can do is we can do the cosine of 240 plus J sine of 240, right? That could be the result that we get. We also can see that over here, it's 60 degrees from the cosine axis. So we can certainly do cosine of 60 degrees plus J sine of minus 30. And that should get us this square minus 0.5 and the square root of 3 over 2. If you don't remember sine of 0 is square root of 0 over 2. Sine of 30 is square root of 1 over 2. And on and on and on and on and on. We can go through that process and we can get those results. Okay? That's how we'll end up with those values there. And then we'll do the same thing for phase C. And you can add those. This is just doing the polar math to go ahead and show it in the X and Y. If you don't like this, you can call it the J term to show that it's the Y axis of that representation. And then we sum them together, and what we end up with, when we add them all together, is 1.5 sine of omega t in the X direction minus 1.5 cosine of omega t in the Y direction. That's what our sum is if we're just doing it generic for this particular problem. And then we already went through this one, how we saw the rotation. But now, hopefully you can see things a little bit different. Look at the red, blue, and yellow arrows. Do they ever change their location? Sometimes they're going straight up, and sometimes they're going in 180 degrees the opposite direction. But they don't actually rotate, do they? They wouldn't, because the physical windings of those of the machine is not rotating. So it is fixed, its location. The only thing that changes the magnetic field direction is you've got negative current or positive current. But take a look at the red, yellow, and blue. They are always going to be in one direction or 180 degrees out of there. Their magnitude might change. They might go up and down, but they're always shown in the same direction or in the opposite direction. Yes, sir.
So The frequency of the electricity generated would be determined by the rotation speed of the motor, right?
Well, that depends. So the question is, does the speed of the electrical frequency, is it determined by the speed of rotation? And the answer is partly. So if you're a generator, it's determined by the speed of rotation and the number of poles of the machine. So it's not just the electrical frequency. All right. So there's two parts to it. But it can be directly determined if it's a two-pole machine. It would be the same. The operating speed and the electrical frequency would be essentially the same.
So this would be a two-pole, right?
This is a two-pole machine. Yep. Why did Aaron say it's a two-pole machine? Can you tell? How did Aaron know that? There's two ways. First way, which might be the obvious way, is look at the currents rotating through 360 degrees. How much rotation of the black line is there? 360, right? We start at 0, then we go to the 360, and it gets back to its beginning point. So 0 or 360 degrees means they're operating at the same speed. That would be a two-pole machine. The other one that might be less obvious is I only have one black line. The black line is the corresponding net magnetic field. That means I only have one north-south pole pair. So those two ways would indicate, where you get the speed of operation. One pole pair, or it takes 360 mechanical degrees to do 360 electrical degrees, or 360 electrical degrees to get 360 mechanical degrees. Either one is the same. All right, so let's swap two out. So do you all remember what we had at the beginning? Let me see if I can slide this out of the way a little bit. We have A, C, B. What did we have before? We had A, B, C. So we swapped B and C. So what happened? Well, the process is the same. Our fingers point in the direction of current, thumbs point in the direction of magnetic field. That's B sub A. B sub B was originally going down. Now when we do B sub B, we wrap our fingers around, and it is now going up in this direction. Same thing for C. C was going up. Now we point, and it ends up going down. So before, this was minus 120, and this was plus 120. Now, our magnetic fields, the resulting directions have changed. All right? A hasn't changed at all. It was at an angle of 0. So let's take a look and kind of walk through the process of what ends up happening. So when we had A and B did the previous way, we ended up with rotation like this, right? In a counterclockwise direction. Let's take a look and see if anything has changed. So we run it at t equals 0, and we've got our current is at 0 degrees. We just run it through. We take sine of 0, which is 0, sine of minus 120, which is negative square root of 3 over 2, b sub m at an angle of 120, and b sub c, b sub m sine of 120 degrees at an angle of minus 120 equals that value. Here's one thing that's very, very important. I have not changed the phase relationship of the current. This is IA, this is IB, and this is IC. That's exactly what we had before, right? So all we did is physically change where winding or current B went into the machine. Before it was going over here, and C was going over here. So I'm kind of, hopefully you can see. So B was going into this part winding, C was going over here. What we ended up doing is this, right? We determined the motor and we reconnected it with our arms crossed, essentially. So look what we get. 1.5 B sub M, we get that 1.5 value. The angle was 0 before. It's minus 90 now. So we don't know anything yet. The angle is minus 90. As long as it rotates around, I don't really care what the angle is. We just want it to rotate it around. Now, let's go ahead and do that at 30 degrees. So 30 degrees, we do sine of 30. We have 1/2 b sub m at an angle of 0. Do it, and we have 30 degrees of current, which is minus 120 plus 30. Now we have minus 90. We have negative b sub m at an angle of 120. And then the last one for C, 1/2 b sub m at an angle of minus 120. When we sum those together, we still have the 1.5 b sub m, but look at my angle. It's minus 60 versus minus 90. Is that a problem? No. We still have 1.5, but instead of operating in the counterclockwise direction, isn't this rotating in the clockwise direction? From minus 90 to minus 60, minus 90 is here, minus 60 is here. Electrically, we rotated a positive 30 degrees. The motor in the previous case, when B and C were configured previously, would go counterclockwise. I mean, would go clockwise. Now this is going counterclockwise. So let me ask you this question. In the real world, if you have a three-phase motor and it's spinning in the wrong direction, what do? You swap B and C. You can actually swap any two phases. Doesn't need to be B and C. It could be A and C, it could be A and B, any one. And so in the real world, if you purchase a skid that has a motor and a pump or a compressor or whatever, and if it's on a skid, it's probably not too big of a deal. But in many cases, you have your electricians wire it up. And then what they do is they decouple the mechanical load to the motor. Why do you think they do that? They do a bump test because the mechanical load might have a required degree of rotation. It might want to always operate counterclockwise. And if you plug it in and you turn it on and it's rotating clockwise, then you might have damaged the mechanical system. So by decoupling the mechanical load from the electrical motor, you bump it, you just energize it for a second, you watch the motor spin and verify, does it flow in the proper direction or the improper direction? If it's flowing in the improper direction, you de-energize, you swap any two leads, and then you pump it again and you'll see it switches direction. So you can get reverse or forward direction literally by swapping any two phases. Super, super easy to do. I love me some MATLAB. So let's do a MATLAB representation. Okay. This is the general way where we've gone ahead and we're just going to do the calculations. Don't super duper worry if this does or doesn't make sense. But you can see I have my three currents. You can see this is ABC rotation, right? A starts at 0, B starts at 240, which is minus 120, and C is over here. You can see that my BA is at an angle of 0. My B sub B is at 120 degrees. So if I go over here, it's this configuration here, right? Minus 120 or positive 120 because I have that over here. And C is at minus 120. So this is my, just my angles associated with the current, the positive currents going through there. And then I just say, you know, whatever, omega T, I'm going to start out at 0 degrees. Here are my three currents. So plugging in 0 degrees because omega times T is 0. MATLAB makes me work in radians. So that's why I had to multiply by pi over 180 because MATLAB would say, oh, and that's not 0 degrees. It would do the calculations in radians. So I'm just showing you how you do the calculations here to convert to radians. So I calculate my three currents, what the actual values are at 0 degrees. Then I'm going to go ahead and calculate what the individual magnetic fields are because of those current flows, BA, BB, BC. Then I'm going to sum those together and come up with a total value. All right. So I'm going to set a breakpoint here. I'm going to run this. And there's MATLAB. So here is, and sorry, I have to do this bigger. So let me do this again. Let me start it again because I didn't have it large enough. Run it. So I don't have the spacing set up correctly, but you can see IA is 0. IB is negative 8.66. And IC is positive 8.66. Those match, if you look at the sine waves where we are with 120 degrees, those should match those values. The BA, because I have 0 current through it, the magnetic field is 0 at an angle of 0. Right, that's where we calculate the angle, but the magnitude of that magnetic field is 0. I do the same thing for B sub B. Now I got 0.866 at an angle of minus 60. B sub C, 0.866 at an angle of minus 120. I sum those together and I get 1.5 at an angle of minus 9. Okay, everybody see that? All right, so now I'm going to continue. So all I've done is rotated 30 degrees electrically. And I want to see, whoops. Did it again. See, I can't see what you guys are seeing on the screen. So let me try that again. Here's the PC screen. And let's duplicate it. There we go. So now you can see my original one was at an angle of minus 90. Now it's at an angle of minus 60. So I went from here to here, which would indicate the direction is counterclockwise. I can do that all I want instead of 30 degrees. Let's say I want it to be 90 degrees. And I'm going to clear my breakpoints. Now I'm going to run it. Wait till this updates. And what do you know? We're still at minus 90 because at 0, it's that value. But now when we go at 90 degrees later, we get a 90-degree rotation. So you can see that the mechanical rotation matches the electrical rotation. If I wanted to swap winding, pick 2 windings you want to swap. You pick. You have A, B, and C. Pick any 2. A and C. All right. So, question for you. Do I need to change these? IA, IB, IC? Nope. Those don't change. What I need to change is instead of the A and the C over here, originally I have this, right? I have A, C, and B, right? Those are the way I have it set up. Let me just double check. B sub B is 120. Yep, and B sub C is minus 120. All right, so this is what I had when I started the MATLAB script. So I've got B sub C, B sub A, and B sub B. Now, as Noah suggested, I'm going to swap A and C. So this is my modified configuration. This is C and C prime, A and A prime, B and B prime. So now if I'm going to do my vectors, this is B sub A. This is B sub B. And this is B sub C. So I'm going to have to go ahead and correct those in here. So B sub A is no longer at 0 degrees. You can see over here, it's at minus 120. So I make this minus 120. B sub B hasn't changed, right? I didn't swap B at all. I just swapped A and C. So there's no work that needs to be done for B sub B. B sub C now is at 0 degrees. So I bring this one to 0 degrees. I have to do it here, and I have to do it here because I'm doing two calculations, right? To compare. Now I'm going to rerun this, and I want to see, did it go from a counterclockwise direction to a clockwise direction? So remember, I started with this one where I started at minus 90 and ended up at 0. Hopefully, I start at whatever angle it is, and then I go in the opposite direction. So let's run it and wait till it brings up the plot. Oh, yeah. Thank you. That would cause a problem. Pi over 120. Sorry, times pi over 180. And I'm going to just clean this up over here. All right, try running that again. Started at minus 330. You can check that here. You can see positive 330 or minus 30 or positive 330 is the same. And then when I rotated 90 degrees, it was minus 120. So it started over here and then rotated here. So I swapped A and C. Before I swapped B and C. So any two phases allows you to calculate and rotate directions. But the magnetic field still stays 1.5. Its value doesn't deviate. Okay, and that's in the real world, that's what electricians do. If it runs in the right direction, then you're done. If it's running in the wrong direction, then you swap it out. Do you remember when we started talking about three-phase towards the beginning of the semester? I said most of the time you don't even care how the machine is wired. Here's why. If it's running in the wrong direction, you just swap them around. It doesn't hurt the motor. It doesn't hurt the electrical supply. It doesn't matter any of that. As long as you're connecting it three-phase, works beautifully. No issues, no concerns. Okay. All right. How about we swap another one? We swapped A and C, at least MATLAB. Let's go ahead and swap B and C. Okay. So we'll swap it from this configuration, right? So this, we've already swapped A and C. So let's swap A and C and then B and C. Everybody okay with that? So I'm not doing anything other than just continuing to swap things. And let's see if I go back in the opposite direction. So I'm going to start over here. This is the base. This is the modify. And this is the modify 2. So here's my shaft. I'm swapping B, A, and C. I've already done that here. So now I want to swap B and C. So this becomes B, this becomes C, and that stays A. Didn't touch A, I just swapped B and C. So that's A prime, B prime, C prime. B sub A has not changed. But now, if I go ahead and run for BC, this is up over here. This was B sub B, now it's B sub B, now it's B sub C. And then lastly, this was B sub C, now it's B sub C. So if I want to swap those again, I can see that A hasn't changed. B sub B is now at an angle of 0. And B sub C is at an angle of positive 120. So 120. and 0. Everybody agree with that? Just by, showing how we change the actual corresponding magnetic field where we get those values. That's where we end up with that. So before we had a rotational direction, we started here at -30, then we rotated down to -120. So we rotated in the clockwise direction. By swapping B and C from this design, from the previous design, hopefully it's going in a counterclockwise direction again. So let's run it. So we can't tell just by looking at these numbers. We have to look over here. It started out at +150 up over here. It's now down at -120. So is that counterclockwise still, or now did it swap directions again? Before, it was over here. Whoops, pick up. How come it won't move up? Huh, the pan's not working. It was over here, and then it went over here, right? Over here now, we have 150, which is up over here, sort of. And now it is down at -120, which is here. It changed direction again. Okay. So we can swap A and C, A and B, B and it doesn't matter. You can swap it in any order you want to change direction. Questions on that? Because this works for a 3-pole machine. I mean, a 3-pole. A 2-pole machine, 4-pole machine, 6-pole machine, 8-pole machine. The difference is we start dividing the machine in quadrants. So when you have a 4-pole machine, you basically mechanically divided the machine in half. A 6-pole machine means you divided it in a third, and on and on and on and on and on. But it's pretty important for going ahead and representing that. All right, before I let you go, let's take a look at the syllabus because we did miss a class last week on Tuesday. Oh, Thursday, not Tuesday. And let's look at some dates. Because what's coming up? On the syllabus, not as in tomorrow. You have an exam a week from yesterday. Exam number 1. Going to cover chapters 1, 2, and Appendix A. So on Thursday, we'll do an exam review because the exam will be Monday morning, bright and early at 8 o'clock, 8 to 11, right? During our lab period. So I've got to find a room number for that, and I'll get that for you. But just to be looking at the schedule, you'll have your first exam next Monday.
Would that be the same time for online?
Yep.
Well,
Yep.
okay.
If you can't make it, we can figure out a proctor, but everybody will do the exam. If you're doing the exam online, if you do the lab online, you can do the exam online. You just have to let me know, and I'll set something up where you can have Zoom. You have a Zoom session, kind of like lab, but your cameras have to be on so I can see what you're doing, etc. But for Thursday's class, we'll do a review because that's our last class before we take the exam. All right. And if you look in the Brightspace folder, you should already see come on, wake up. You should already see under the content for that class. I haven't updated yet. This will be the 220 update. Well, actually, I'll just delete it because this is actually going to be not 220. This is going to be after the exam. So 220 has the exam 1 review already posted. So it's already available to you. For today's class, I'll upload these files. Let's see, under MATLAB, the ones we did today. And if anybody wants, you can play around with the MATLAB files if you want. I just think it kind of helps sort of figure things out and kind of display and figure out what's happening. But yes, that is the syllabus tells you we have an exam coming up. You get one 8.5 by 11 sheet paper, and you can use MATLAB or here's a key thing, or your calculator, not hand.
That paper double-sided?
Double-sided. So you can bring your calculator or MATLAB, and I'll bring all the scratch paper and all that stuff. So for Thursday, try to come with some questions. Take a look at the exam review. It's got, some of the highlighted topics that we've covered already, and then giving you an idea of the type of questions are going to be on the test. Go from there. Questions on anything? Yes, sir.
Like the homework problem?
More or less. Yep. Very similar. Not exactly, because it's not homework, it's an exam. So we really want to see what you've learned. And so there'll be, not the exact application, but it should be similar. Okay. Any other questions? I'm done sooner than I thought. I thought there'd been a lot of questions on the MATLAB scripting and all that stuff, but I don't know if you all are a fan of MATLAB yet. Maybe someday, but someday. Well, again, MATLAB, like I said, I know it looks like there's a lot of information here in this, but I really, if I'm just doing calculations, I really only need this stuff right here. I do that, and then I rinse and repeat again with omega t, and I can just do it that really quickly. So with MATLAB, I can get those results really, really fast. Your calculator, you have to do it by hand, and it just takes time. And the advantage to doing it with MATLAB keeps me honest. When I put this clear CLC, and I think I've talked about this class before, that clears all the variables. So when I run it, you can't say, hey, you just brought these numbers in from no man's land. No, it actually was calculated out because clear clears all the variable. If you look at, I'll run it here real quick. If I type, and I got to bring the workspace here real quick. So if I show, where's my view layout here? If I want to see the workspace, these are all the variables that are stored in MATLAB. So if I wanted to be sneaky, I could just, pre-populate these variables with the results I want. Look what happened when I type clear. Oops, when I type it correctly. Those are all gone. So it doesn't know what those variables mean anymore. So when I run a MATLAB script file with clear in it, that means it's starting from scratch. The CLC, I'll just show you what that is. That just clears the command window. So it doesn't have a lot of extra material. Like clear is the one that keeps me really honest. So that's why, again, I like to have that there. Okay, any questions? No questions? So it won't be lab on Monday because we'll be giving an exam, right? So no lab. Yes, sir.
Are you going to post the homework answers?
They are not there already?
They automatically populate.
I have a date that comes up.
Oh.
Well, after a certain date. So you see how it says it starts at February 18th at 12:30. So that goes because the homework was due today at the beginning of class. So that is available to you 30 minutes. Yep. So that'll show up automatically. Forgot to share my screen. Let me share my screen again. So you all can see what I'm seeing, or that the students in the class are seeing. But if you look at the dates, you can see that that's going to be available 12:30. You can't click it. Yeah.
Yeah.
Okay. All right, anything else? Feel good, feel bad, feel okay? Still have time? All right, there's nothing else. Have a great day. Try to stay warm. It is cold out there. And I will talk to you all later. Take care, everyone.